looking for all the integers n and k. Primary, we're just interested in k really, but such that these three arithmetic functions are related in this fashion. This is the Euler Phi function. It counts the number of primes, the number of integers less than or equal to n that are relatively prime to n. For example, a simple example here, which will actually come up, phi at any prime. And you could almost define, if you define the phi function first and prime numbers second, you could define prime numbers this way. Phi of any prime is equal to p minus 1, because by definition, all the numbers less than or equal to any prime number don't have anything in common with a prime number except for 1, okay? But so you have 1 and everything's relatively prime, okay? Except for 1, okay? So, but anyway, there's p minus 1 of them, I guess, if that's a better explanation. There's p minus 1 values less than p that are relatively prime to p. And again, you could define a prime number this way if you define the Euler Phi function first. Now, y'all, this one over here is more frequently these days called the tau function. And this is the number of divisors functions. And let me just write an example here. Tau, that is not the way a tau is made. But say, for example, tau at, and I'll use p again, just general case. Tau at p, there's only two divisors of p, since it's a prime number, right? Namely p and 1. Okay, so this is equal to 2. Okay? And then sigma just sums up the divisors. I won't do the example of that in the name of getting along with the problem. But this is the sum of the divisors, sigma. This is the Euler Phi function. And this is the number of divisors function. We're looking for the number of, we want to find all k less than 135 such that this equality holds. All right, now this is a fact that's a problem all in of itself. I call it a fact. It's a theorem that you could actually prove. It's easy to see one way, but you can see why this fact would be related to this problem, okay? There's no doubt that this is certainly connected in structure to the problem we're trying to solve. Now, just an example of one direction. I think going from left to right is a harder proof, but going from right to left here, if you want to assume that n is equal to p, okay, we just saw right here, this is p minus 1. Now, this one here, y'all, this is the sum of the divisors. Well, the only divisors of p are 1 and p, so that sum must be p plus 1. Okay? Now notice, and again, yeah, I'm showing you just from left to right. Okay, I'm not asserting equality. I'm just showing you from right to left that this thing holds. So now, so that's what you get on this side, and this is certainly equal to 2p, right? Okay, now over here, it's clear, okay, that this is also equal to, and I'll write it like this, p2, right? Does that mean the same thing, right? So you see, this is a proof, assuming n is prime, that this condition holds. It's kind of fascinating that this happens, you know? But I think the proof going from left to right is a little bit harder. I'm going to omit it. I don't really know how to do it. I'm going to think about it. But anyway, I got this from a Charles Vanden Eynden number theory textbook, this particular problem. There's two versions of it, one going to the right, one going to the left. I think problems 37 and 38 in one of the sections. Okay. Now, so this fact implies that k over 12 must be a prime number. Okay, n equals k over 12 technically. You see, you're just eyeballing the coefficient of d of n. K over 12 must equal to n, right? So hopefully that's clear enough. Hopefully I'm not overlooking anything there. But anyway, that means that n must be a prime number, right? Based on this fact, of course, right? This relationship is never going to hold unless n is a prime number, okay? So here you go. You just list out all the possibilities, folks. K over 12, not k, must be a prime number. K over 12 is n, okay? So so k over, right here, we get 24 over 2, and I'm just, notice I didn't list 12 over 12, because that's just 1, and that by definition, it's not, or by convention, it's not a prime. So 2, 3, that's looking good. Notice this isn't a prime. So we have to scratch that out, right? That's 4. This is a prime. Okay, this is not a prime. Scratch it out, exit out. This is a prime, 7 times 12. This is not a prime. Also, the 9 that follows is not a prime. Of course, 10 is not a prime. And right here, we get the last one as far as our constraint goes. 11 times 12 is 132, so we have 11, right? And of course, right here, we've exceeded, remember, that's why I did this. This seems kind of arbitrary, but this would go on and on and on unless you gave a constraint here. So in other words, the answer to the problem would be these values of k, and of course the corresponding values of n are just prime numbers, right? So this one would be one of the k's. 36, 60, okay, what else? 84, and 132. So y'all, that's the answer. I'll just put QED. We didn't prove anything, but but we're done right now with the problem, because these are the K's, and the primes 11, 7, 5, 3, and 2 are the attendant or the concomitant prime numbers associated. Okay, so y'all, I like this problem, and I think the more substantive part of the problem, I composed it just to see if it would amount to much, and it's not a great problem, but it's just, at least it takes advantage of a fact from a number theory textbook, which is trivial one way, but again, I'm not quite sure how easy it would be to go assume this left-hand side is true and show that that you get n being a prime number, okay? Or not the left-hand side, but meaning if you assume this whole equality is true, okay, that would you would have to prove that n is a prime number. Again, I showed it to you in a almost trivial way. If n is a prime, then it easily works out, right? Okay, but otherwise it doesn't. So it's kind of interesting you may want to think about that, how to prove moving from left to right. Okay, all right. Good day.